All right, 2003 Form B, problem 2 says the figure above, or to the right that is, shows the graphs of the circles x squared plus y squared equals 2, and I hope it makes sense that the one centered at the origin would be x squared plus y squared equals 2. Here's one shifted to the right one with a radius of 1, and so I hope it makes sense that that is the smaller one here to the right. Okay. The graphs intersect at the points 1, 1 and at 1, negative 1, which I don't think I'll personally use that piece of information, but that's nice of them to mention it. Let R be the shaded region in the first quadrant bounded by the two circles and the x-axis, so as seen here. For part A, set up an expression involving one or more integrals with respect to x that represents the area of R. So my plan for part A is to use kind of the idea of the upper minus lower approach, but you'll have to change the definition of the upper function when you get to 1. So I would use a 2 integral approach for part A. Okay. In addition to that, I would need to make sure that I have the appropriate functions in terms of x to put into my integral. So for starters, let's get a function rule for the top half of this smaller circle. So that would mean that I would isolate y here, and then when I square root, I'm going to purposely choose the positive version so I get the upper half as opposed to the bottom half of the circle. So let me get started there. So x minus 1 squared plus y squared equals 1. I'm going to subtract the x mess over to the other side. And then I'm going to square root both sides. I'm going to consider the plus or minus, and then I'm going to make an educated choice as to which one makes the most sense. Since I do want the upper half of the circle, it makes sense for me to choose the positive version, not the negative version. Hopefully that makes sense. Okay, and so now for the function rule that would represent kind of the upper function here in the second part of region R, the one that goes from 1 to square root 2 here. And so that would be the upper half of this circle. So I'm going to do the same thing, isolate y, and then purposely choose the positive square root version. So okay, so I'm going to purposely choose the positive version and rule out the negative version. Okay, now to set up my area, I would do the integral from 0 to 1 using this expression for the upper with respect to x, and then I would add the integral from 1, and you could algebraically solve for that x value simply by putting 0 in for y into the equation and solving for x. You'd find that it's positive square root 2. And then I'll be using this expression for this piece. Like so. Okay? So let me show you, actually I think we'll do scoring guidelines at the end. There are a couple of alternative ways to do these. I'm just going to show the most expected ways, so I think I'll do the scoring at the very end. Okay? All right, for part B, set up an expression involving one or more integrals with respect to y that represents an area of R. So now I get to plan it, but you have to kind of like imagine that we're turning it and we're adding up these kind of values as we scan the y-axis from negative to positive. So what we're going to need to do now is get a function rule for the right half of this circle in terms of y. So we're just going to isolate x on this expression, and then I'm going to purposely use the positive square root again so that I get the right half of this graph where the x coordinates are positive. So, so that would look like this. Let's see, we're going to isolate y, no, x, sorry. So we're going to purposely choose the positive and rule out the negative on that one. Okay? All right, but good times. I'm going to need to do kind of a right minus left type deal. So I'm actually going to need an expression that represents these values right here. And so what that means is that I need to isolate x again, but on this equation. But notice that this is the left half of that circle. So when I square root, I'm going to purposely choose the negative version of the square root when I go through that work. So it would look like this. X minus 1 squared, I'm just going to subtract the y squared over to the other side. And then I'm going to square root both sides. So I'd have x, oops, I don't need parentheses anymore. I'd have x minus 1 equals plus or minus square root of 1 minus y squared. And then you can add the 1 over. Okay, and I hope it makes sense that if you have 1 is right here in the middle. If you add stuff, you get the right side of the circle, but if you subtract stuff, you get the left side of the circle. So that's why this time I'm going to purposely choose the negative version and rule out the positive version. Okay, now for my formula for area. I think I'll put it here. My area would be, okay, so I'm going to do right, which is this expression, minus the left, which would be this expression right here, with respect to y. And then the bounds, you want to start adding those at 0 and then stop adding them at 1. Hopefully it makes sense. Make sure you always scan your axes from negative to positive, or in increasing order, essentially. Okay? All right, my friends, that would be my setup. Again, there's, let's see. Actually, no, I think that's pretty much what they're expecting for that one. I don't think they mentioned any other answers for that. Okay, now let's look at part C. Part C says, the polar equations of the circles are r equals square root 2. I'm going to take all this stuff off. Okay, so I hope it makes sense from your experience that it's the one centered at the origin that would equal r equals square root 2, and then r equals 2 cosine theta, that would be this one. Okay, set up an expression involving one or more integrals with respect to the polar angle theta that represents the area r. I'm going to go ahead and do a 2-integral approach. There's also a really simple single integral approach where you just use some basic geometry, but I'm just going to make sure that we're good with integrals in this respect. So basically, make sure that you remember that when you're using integrals to find area in polar form, your integrals are always going to send infinitely many, infinitely thin little sectors that start at the angle that you give and stop at the upper bound angle, okay? So I want you to notice that since that's how they work, that I would, if I'm going to use a single integral, I would have to use 2, because the way the r is defined for a region r would change after this angle right here. And what is this angle right here? Well, if that's the point 1, 1, I hope it makes sense that that's a 45-degree angle. You could always use conversions between rectangular and polar to figure that out as well. But like you'd use tangent of theta equals y over x, you'd get tangent of theta equals 1 over 1, so theta would be pi over 4. So I hope it makes sense that that angle right there is pi over 4. Okay, so my first integral that would basically solve for this little wedge here would be 1/2 times the integral from 0 to pi over 4 of r, which would be square root 2 squared d theta, plus. Now I'm going to keep going, but once I pass pi over 4, I don't want to use square root 2 for my radius anymore, because I'm going out to this circle right here, and that would be 2 cosine theta. So this time I'm going to have 1/2 times the integral from pi over 4 to pi over 2 of r squared d theta. There we go. Okay, directions said we did not have to evaluate anything. We were just supposed to set up integrals, which is super fun. So now let's talk about scoring. So here are the scoring guidelines. These are things you can always look up. All you have to know is that we're working from the Calc BC test now, and that, you know, you put the year in, the form, and then you can find all the scoring guidelines, okay? So you can see for part A, you have 1 point. Well, first you can see, if you need to, pause the video. If you had a different answer than I did, you can see they have another possible answer here. But 1 point for the integrand for the larger circle. Let's see, where was that? Integrand for the larger circle. There we go, 1 point for that. 1 point for the integrand or geometric area for the smaller circle. Oops, actually I think I have these backwards, whatever. 1 point for your integrands, essentially. 1 point for your bounds, and it needs to be true for any integrals that you have. So 0 to 1 and 1 to square root 2. So 1 point for bounds. There we go. Okay. For part B, you can see that they only mentioned one answer, and it matches the answer that I have. It says 1 point for the limits, so, or bounds. And then it says 2 points for the integrand. Okay, now they've got some little partial credit ideas. So -1 for reversal, that's if you had these but you had them backwards. -1 if you had the right idea but you botched something when you were solving for x. -1 if you have a plus sign there rather than subtract. And then a -2 for any other error. No points for any other error. So hopefully that makes sense. Okay. Part C. Let's see. Part C says 1 point for the integrand or geometric area of the larger circle. So you totally could have used geometry for this first part. So 1 point for either setting up the integral or doing a little, just, you know, 1/8 of a circle type geometry stuff for that part. And then 1 point for the integrand for the smaller circle. That would be here. And 1 point for the limits on the integral. I kind of think that they're including the 1/2 as part of the integrand, to be honest with you. But there you go. All right, my friends, that's where the 9 points are from. I hope this makes sense, and I hope that you're off to at least an okay start. Don't forget to celebrate every point. Take care, everybody.